So we can expand this polynomial multiplication, and then we just equate coefficients that we want to have. And this induces the following linear constraints, which is quite a bit. And then solving, it yields that the missing polynomials are just x squared plus xy plus 1, and y squared minus 2 are the missing terms. Yes, because our original polynomial was the original terms in the ideal was x squared plus xy plus 1 and y squared minus 2. So it's actually x squared minus xy plus 1 and y squared minus 2 are the what we need to multiply by. Okay. So no, I'm sorry. It's actually x squared minus xy plus 1 and x squared are the missing terms that will prove that that x squared plus 1 is in this particular ideal. But notice that one thing, this is a little bit crude, and the problem is that if the polynomial is non-ideal, we're going to search forever. So, and we don't want to do that. We want this to terminate, and we want to be able to decide always. So the other approach is Grobner basis. So we're going to first define an order, and we're going to form a Grobner basis, and this will give us a certain beautiful property, and then we can prove that we can always take, for some finite set of polynomials, find an equivalent Grobner basis, and this will solve all our problems. So to define a Grobner basis, we first define ordering on monomials. So given a monomial x1 I1 up to xn in, we say it's less than this ordering x1 j1 up to xn jn if the sum of the ik is less than the sum of the jk. But and in the case that the sum of the ik is equal to the sum of the jk, then we take then we represent them as vectors of natural numbers, and we take the one that appears before the other reverse lexicographically. So, for example, the vector 2, 1, 1 appears before the vector. So it appears. The vector 2, 1, 1 appears after 0, 3, 0. So when you look at this example, the x12, x2 will be less than x2 cubed, because even though their multiple degrees are the same, 2, 1, 0 appears after 0, 0, 3, 0, and we're ordering by reverse lexicographically. And of course, for the first example, x2 squared is less than x1 squared x2 because of the multi-degree is lower. And multi-degree, once again, is just the sum of the exponents of the variables. So now we're going to define a reduction system given a set of polynomials S. And for some reason, logic, we always love to define reduction systems, show that it always terminates to an irreducible and beautiful, nice things happen. And I just love learning about reduction systems, whether it's about some strong normalization of some system, or is it just, I love it. And the proofs are always very difficult. And the proofs of the termination of this scheme and a bunch of nice properties, I refer to Harrison in the chapter in this section. I believe it's in the current section. So we're going to define a reduction system given a set of polynomials S. So we say that P, we define a one-step reduction, P to P prime under S, if polynomial P contains a monomial M such that for some polynomial H plus Q with maximal monomial H under the less than then the order we just gave, then we can write P prime equals P minus M prime, H plus Q equals P minus M prime Q, where M equals H times M prime. So this is a little bit technical, But the intuition behind this is that we can take the head monomial for an element of the set, right? The set S. And then we can rewrite it. And then whenever we can write it as, whenever we see the head monomial in a polynomial, to reduce it, we just replace that polynomial, we replace the head monomial, the biggest monomial. And when I say biggest monomial, it's the biggest, yes, occurring in S, or the certain element S. And we can replace it with the minus Q, where H plus Q where that element equals, where is it? Okay, sorry. So maybe I can illuminate this with an example. So we have, for example, S equals x squared minus xy plus y, and we have in there, and we want to reduce the polynomial x4 plus 1. So we have the head polynomial is x squared, because that has the highest, in the ordering that we just gave. It has multi-degree 2, and it occurs before, and it occurs reverse lexicographically to xy before it. So I mean after it. Yeah. So x squared is the highest, and we know that. So that's h equals x squared, and we also know that q equals minus xy plus y, because that's the remaining of that term. So intuitively, what we do is we set xy minus xy plus y equals 0. We solve for x squared, and then that gives us a lower, yes, there we go, a lower polynomial in the ordering. And what this does is that we can replace in the original polynomial all elements that are of the head polynomial with a strictly smaller monomial, which is what we just did, which is going to be negative q, yes. So intuitively, we replace indices of h equals x squared with minus q equals xy minus y. And Harrison goes on to explain this intuition of why this technical definition reflects this intuition. And the example it gives is that starting with the polynomial x to the 4 plus 1, we can do a one-step reduction and take x squared of x to the 4 and replace it with xy minus y. And then we do some polynomial, we distribute the x squared, and then we do another one-step reduction and replace the x squared with xy minus y. And once again, we distribute. And then we can do another one-step reduction and replace the x squared with the minus q xy minus y, setting it again. And then we perform one more, like we see another x squared term. We see, another x squared term, which is the one that occurs before the y. And this will finally give us xy cubed minus 2xy squared minus y cubed plus y squared plus 1. And since we no longer have an x squared power, this guy is just irreducible. We can't go any further. So that's how, and we use the star notation, and we say that this is the term that it finally reduces to under, or the term that it reduces to under these one-step reductions. So we're going to define a set of polynomials f as a Grobner basis for an ideal j if j equals idq, and it's generated by the polynomials f, and the reduction system f is over the set f is confluent. And recall that confluence is just when you do the reductions, and if you take different paths, you can just meet up again. It's it's a nice commutative diagram with Newman's lemma. I liked it. But let's, so yes, that's confluence.